So welcome to chapter 10. We're going to be kicking off our content and chapters about liquids and solids, and we're going to start by talking about bulk phases and what that means for intermolecular forces. So when we generally conceptualize chemistry, we are thinking about things in terms of molecules. We spent a lot of time in General Chemistry 1 talking about what the changes that molecules do, how we write chemical formulas for molecules, how we come up with structures of molecules. So, for example, water is H2O. And we know that H2O as a kind of a listing of the atoms in the compound can be translated into a Lewis structure to describe the actual connections between atoms in a molecule. But you don't interact with single water molecules. Instead, you interact with what are called bulk phases of a substance. So for water, that could be something like liquid. Phases imply solid, liquid, gas, and bulk means a lot of molecules, basically multiple molecules together. So water in a bulk phase is commonly a liquid. Could also be a solid ice. Okay, and so we normally conceptualize or define these molecules or compounds as molecules, but there's a lot of water molecules together. And so we could potentially have, the properties of a single molecule, but what about the properties of the substance or the phase that forms when you're putting a lot of those molecules together? What are those properties and how does the molecule inform those properties is what we want to talk about. So we're going to start by looking at what the phases of matter are. We have gases, liquids, and solids. And these different phases of matter are going to be defined by what the kind of relative positions and movement of molecules are for those phases. In gases, the molecules are very far apart. They don't touch each other. Instead, they just kind of move. Solids and liquids then are linked or similar in the fact that the molecules are touching each other. So usually when people talk about bulk phases, that's what they mean, these solids and liquids, because in these cases, you are looking at situations where molecules are touching each other and there's going to be interactions. The differences between those two phases are then between solids where the movement of molecules is highly restricted, whereas in liquids, there's much more movement. The molecules are able to flow over each other. So these sort of microscopic depictions of what the phases of matter are lead into and inform what those phases of matter look like and the properties that we experience. Solids, the molecules are really restricted in their motion. They're kind of jammed together. They are firm. They can't move, just like solids don't have free motion, right? There's a rigid structure. They have a shape. The reason why you can't see the bits of ice move or they don't fall apart is because the molecules don't fall apart. Then for a liquid, the reason why a liquid flows is because the molecules are able to flow over each other. Then gases can, move up seemingly just kind of floating around because the molecules aren't bound together. They can move as well, just kind of floating freely away from each other. They will fill whatever space they're allowed to fill. So what informs why and how these different sorts of bulk phases form or have these properties, right? We can have solids, liquids, and gases of any given substance, so what goes on in terms of informing when and why and how those different bulk phases form? And the answer is going to be intermolecular forces. So if we look at this word intermolecular, so inter means between, like your interpersonal skills or how good you are at relating to other people. And so intermolecular forces are interactions between molecules. So when we've talked previously about chemical bonds, forming Lewis structures and those sorts of ideas, those are intramolecular force. That's a fancy way to say chemical bond, because those are within molecules. Those are what hold molecules together. So these intermolecular forces, these are going to be interactions between molecules. It's important to note all of these intermolecular forces we talk about, we are not going to break chemical bonds. What we are going to be looking at is how do two molecules interact with each other, and how do they arrange in space to minimize or maximize those attractive interactions. Kind of how do they arrange. But importantly, chemical bonds are not going to break. Once you have a chemical formula, that Lewis structure, that's going to stay the same. Just kind of how do they orient in space? How do they flow over each other in a liquid? How do those molecules kind of rigidly pack in a solid, or maybe ignore each other in a gas? So if we return to this states of matter, solids, liquids, gases, right? We know that there's kind of two different trade-offs that we can have between them then. We have kind of this idea of how much the molecules move, and then we also have this idea of how close the molecules are to each other. So the closer molecules are together, the more intermolecular attraction you can have. So in a solid, for example, there's not much motion. The molecules are very rigid. You're packed in some sort of pattern like this, where the molecules are all sitting there. And they can arrange in such a way that they are maximally attracted to each other. The opposite end of the spectrum then would be the gas, where the molecules don't touch each other. There is no intermolecular attraction, and instead, motion is the dominant factor. Gases are described entirely by the fact that the molecules are just moving around independent of each other. If you remember, that's that ideal gas law idea. The fact that the molecules don't interact with each other, they're just kind of floating around. So liquids, kind of Goldilocks-y, are right in the middle, a little bit of both. The molecules are still touching each other, so they're interacting with each other, but they're still able to move. So it's not necessarily optimal interactions. Okay, so we can see there's kind of this pattern that is generally true for any substance moving from a solid to a liquid to a gas. There is an increase in motion from solid to liquid, and a really big increase in motion from liquid to gas. So there's more molecular motion. That means there has to be a removal of intermolecular attractions. They can't line up and be attracted to each other anymore. This has some implications for how those sorts of phase transitions happen when we're looking from solid to liquid to gas. When we're going solid to liquid to gas like this, we know that we're putting in more motion. More motion means more energy. The molecules are moving more freely, bouncing around. So phase transition, solid, liquid, gas, are always endothermic. Energy goes into the substance. It goes into driving the motion. You can see these molecules are nice and kind of, there's no motion lines in the image. There's a bit more motion lines in the liquid, and then there's lots of these motion lines in the gas. The molecules have a ton of movement. And so it is always endothermic. It doesn't matter what the substance is. This is water that's shown here, but solid to liquid requires you to put energy in. You can think of like, melting something, and then boiling. Again, you heat something up to boil it. So the opposite processes going from gas to liquid and then liquid to solid are exothermic. The energy leaves the substance. It will always be exothermic. There's always going to be energy leaving the substance in order to do that because they stop moving. The molecules stop moving. They slow down even more, right? And so that's that sort of exothermic loss. The energy leaves the substance. It would go into whatever the surroundings. Molecules are moving less. It's exothermic. The molecules in the surroundings would start to move more, but the water in this case is moving less. So these energy changes are pretty big, and actually the fact that evaporation, going from liquid to gas, is always endothermic, is actually the major way that humans cool. Naturally, this is what sweat does. So sweat gets onto your skin and then it evaporates. And the evaporation of sweat drives cooling. One of the ways you can think about it is that those molecules in the liquid are just kind of bouncing around. The molecules that are moving the fastest, that are driving high temperatures, fly out into the gas phase, and then you are left with, cooler water on you that cools you off. The same thing happens in an air conditioning unit. It's a bit more complicated. You don't just say put out some cold water. But the evaporation, you have a coolant that's flowing through a system that goes through phase changes. Basically, you do an endothermic phase change that's outside, and exothermic that's outside, and endothermic phase change that's inside. So you're going back and forth between a solid and a liquid and a gas in these pipes, and you do it inside where you release cold, and you do it outside where you do that heat. So you're kind of just going back and forth. That's why like the blower out here that's outside blows super hot air. That's why, because it's the heat that was coming out. So one of the ways that you can think about how air conditioners work is you're not actually pumping cold air in, you're sucking hot air out of the house. That's really inefficient. That's why it costs a lot more to cool than to heat. Same idea in refrigerators. That's why the back of a refrigerator is really hot. You're just pumping all the heat out of what's the inside of the fridge. All right, so these phase changes, we know there's kind of these rules, exothermicity, endothermicity. And so you're always putting in energy. And so the question is, these phase changes happen at temperatures. And so we know that a higher temperature that's required for a phase change implies that more energy is needed, right? There's more energy needed to, say, go from a liquid to a gas or something like that. And so higher temperatures for phase transitions imply that there are stronger intermolecular forces. Right? These temperatures are unique for a given substance. And if you think about what's going on here, moving from, say, a solid to a liquid, you're having to break up those attractions. Going from a liquid to a gas does a lot, right? These molecules are all touching each other. This is empty space in between. Those molecules have no more attractions to each other, so you're losing all of those intermolecular forces. A molecule that has strong intermolecular forces will require a higher temperature in order to undergo phase transitions. So we can understand this is answering the question of why are different things, solids, liquids, or gases, at room temperature? Or why is it really difficult to boil water? Why is it really, really difficult to, say, melt glass or something like that? It's because they have really strong interactions holding them together. And so it requires a lot of energy to overcome those and introduce that movement. Because when you're moving to these liquids and gases, there's more movement, there's less intermolecular attraction. So let's look at applying this kind of in a way. So we want to arrange the following compounds by the strength of their intermolecular forces. I have krypton, which boils at negative 153 degrees Celsius. Sucrose melts at 186 degrees Celsius. And octane is a liquid at room temperature. So if we want to be thinking about arranging these molecules by their intermolecular forces, based off the information that we have, it's all going to be about the phases. Okay? And so we know that solids at a given temperature, things that are solid, have stronger intermolecular forces than those substances that are liquid and then those substances that are gases. So we know that this is true, that for a given temperature, this would be the case. So the temperature we're going to choose is room temperature. Krypton boils at negative 153. Room temperature is quite a bit above that. And so it's a gas at room temperature. Sucrose melts all the way up at 186. So that's a solid at room temperature. And then we're told that octane is a liquid at room temperature. So we know that things that are solid at room temperature have stronger intermolecular forces than liquids and then gases, respectively. So that tells us that sucrose is a solid at room temperature. Sucrose has the strongest intermolecular forces. Octane has a liquid, would be the next weakest, and then krypton finally would have the weakest intermolecular forces of this bunch. So you can always make this distinction. Between two gases, we can't do anything yet. And right now, we don't know what krypton, sucrose, or octane are for right now. We could have looked up what these molecules were, their formula, structures, and stuff. But for now, we just know that, hey, we can predict based off the phases. Everything that's a solid has stronger intermolecular forces than the liquids at a given temperature. So we can start to see that intermolecular forces are going to have a determining effect on these properties of these substances, whether or not something's a solid or a liquid or a gas, kind of a fundamental aspect of its physical properties of the substance. And so we're going to talk about some different types of intermolecular forces. There's various types of them that we're going to talk about that are all attractive. There are repulsive forces, but they're more of just like two molecules can't literally be on top of each other. There's nothing that's going to push them away if they're not touching each other. And so the underlying physics of what attracts molecules together is the attraction between positive and negative charges. Just like what holds electrons around atoms and what holds atoms together in molecules, it's all about the attraction between positive and negative. Protons and electrons are still the underlying physics there. So before we're going to move into defining what these types of molecular forces are. Before we do that, we're going to talk a little bit about some background as to how kind of related to these positive, negative things and how we diagnose those. Look at that, we are starting on chemistry for our first. Got a couple of videos here. No participation questions yet. Those will be for the second set of videos that is due for later in the week. Participation assignment due Friday. We got to watch a couple of videos here. Then on Wednesday we'll meet on campus to do lab. And then also the midweek 1 homework will cover these sets, these few videos over on Active. You want to make sure you get your account set up, and then the introduction discussion board over on Blackboard, kind of getting started in class. Instead of a participation assignment for this first set of videos, we've got the introduction discussion board. If you have any questions about anything, let me know. Otherwise, we've got a couple more chemistry videos left. I'll see you there.